Hey you guys, wanting to make you another better video of this electrochemistry chapter 18 that we're supposed to be starting online today. There's a lot of good videos out there if you want to look at those, but I thought we'd go through my PowerPoints that I have for this class that talk about balancing redox reactions. So this is kind of a cool chapter. I always like it because it's really explains a lot of things that we see around us, such as the corrosion that you're seeing right here. This is also known as rust. Having some fun with these things. This is rust. This is corrosion. It's an electrochemical process, which means there's an exchange of electrons. So if you thought you were finished with that out of chapter 4 of Chang chemistry, you are not. We're going to look at it again. What we're going to do is measure EMFs. EMFs are called electromotive force or voltage. You see voltage is right over here. Volts is what we're going to measure our energy exchange in. So anyway, let's get to it and see how this balancing of redox reactions work. But first, let's talk about an electrochemical process. An electrochemical process is oxidation reduction. And when an oxidation reduction reaction occurs, electricity can be produced. And actually, electricity is always produced. It's just whether or not you've been measuring it. We may have seen in previous classes or even last semester when we would dip a metal into another metal solution and you would see metal kind of growing on the outside of the other metal. And that was a redox reaction occurring, but it was within the same test tube, if you will. So an electrochemical process is where energy is released by, it has to be spontaneous. It isn't always spontaneous. We can make it spontaneous, converted to electricity. Or electrical energy is used to cause a non-spontaneous reaction. So that's like a rechargeable battery. This is where a spontaneous reaction is occurring, such as in the battery discharging, or non-spontaneous is rechargeable. I just like circling stuff. Okay, so let's look at an example. Magnesium and oxygen to make magnesium oxide. You can do this in a crucible. You just burn magnesium and this is what happens, but this is a redox reaction. It consists of an oxidation reaction and a reduction reaction. So if you recall, oxidation is where electrons are lost. Reduction is where electrons are gained. But to figure that out, we need to do redox numbers. You see the redox numbers showing up right here. Magnesium, all elements are 0. Magnesium oxide, +2 for magnesium, -2 for oxygen. So that's a redox process. Let's go to how to do redox numbers. So for oxidation numbers, recall that's the charge an atom would have in a molecule if electrons were completely transferred. Of course, this is true in covalent compounds. But if it's a free element, oxidation number of 0, all these are free elements, even if they're diatomic. In a monoatomic ion, the oxidation number is the same as the charge, as in these examples here. So a lithium +1 is +1, 3+ is 3+, and so on. If it's oxygen, it's usually -2, 99% of the time, unless it's a peroxide. Because remember, a peroxide looks like this, where those oxygens, this is so fun, where those oxygens are stuck together. And then if we look at them individually, the oxidation number on each one is -1/2, -1 instead of -2. A superoxide is -1/2. It's O2 -1, and then the oxidation number of oxygen as superoxide is -1/2. That's where I was almost going there for a second. So anyway, let's keep going here. If it's hydrogen, and 99% of the time it is +1, unless it's bonded to metals, and then it's -1. Of course, your alkaline metals are +1 all the time. Alkaline earths are +2, and fluorine is always -1. The sum of the oxidation numbers should equal the charge on that substance. Whether if it's an ion, it should equal the charge on the ion. Look at this bicarbonate that we're going to do an example of. Bicarbonate has a -1 charge. Let's figure out the oxidation numbers for all of them. We have to assume 2 to get the other one, so we are assuming oxygen -2 and hydrogen -1. So you see here, once you do a little algebra, you come up with a +4 oxidation number for carbon. Out of balance redox reactions, what's weird about this is that it's kind of like normal balancing, but not. You have to take into account oxygen and hydrogen being involved, considering these 9 times out of 10 are taking place in an aqueous environment, and that aqueous environment can be acidic or basic. Now, the first slide that you saw, magnesium plus oxygen, that one was not in an aqueous environment. Remember, it was just magnesium plus oxygen to give magnesium oxide. This was not taking place in an aqueous environment, and since it wasn't an aqueous environment, we didn't have to worry about oxygen or hydrogen showing up or disappearing. But all of these are in an aqueous environment, so we have to keep track of that. That's what we're doing now. So in this example, we're going to write the skeletal equation. That skeletal equation is given in this word equation up here. Iron 2 is being oxidized to iron 3 by chromium in dichromate. This is the dichromate, 2-chromium-3 ion. So we first write the skeletal equation, then we identify who's been oxidized and who's been reduced. So you can see that iron has gone to iron 3, chromium has gone to chromium 3. You have to figure out the oxidation number for chromium in dichromate. So the oxidation is the easy one, that's of the iron. The reduction is the chromium going to chromium 6 going to chromium 3. If you do a little calculation of this, you'll see that chromium has to be, let's try it, has to be positive 6. So I'm going to multiply that times 7. That all has to equal negative 2. So if we do our little math here, we get 2x is equal to 12, and x is equal to 6. Perfect. Okay. So now we can just keep going. This first one, iron, and there's no oxygen or hydrogen being exchanged in this iron one, but in the chromium there is. So in this one, there's one, in the iron, there's 1 iron and 1 iron. In chromium, there's 2 chromiums and only 1 chromium. That's what's being balanced right here when this 2 is input. We didn't have to do anything with the iron. Let's go to our next slide here, where now we have to worry about the hydrogens and the oxygens. In the chromium half reaction, we saw that there was oxygens that seemed to disappear, but they didn't. They went into the aqueous environment and turned into liquid water. But then we have to make sure we keep track of those hydrogens. There they are. We just add them back in. It's an acidic environment, so we use hydronium. Now this half reaction is balanced. At this point, charge needs to be balanced. So iron 2 going to iron 3 is an oxidation. That's why you see the electron being added as a product. The chromium being reduced is a reduction, so we need to add the number of electrons such that the charge would balance itself. So this one was positive 6, and this one was positive 3. So to get to positive 6 to positive 3 is 3 electrons, but there's 2 of them, so now we have 6. In order to add these half reactions together, we need to equalize the number of electrons on either side, multiplying that first oxidation reaction by 6, leaving the reduction reaction as is, and now we can add them together. And that's what's happening right here. Now we are finished. Since we're in an acidic environment, we are finished. We just have to make sure that our charge balances, and that's what's happening right here. If you look, both sides have a charge of 24. So this is kind of a little bit more advanced balancing because you have to take into account the charge as well as the number and type of atoms. Now, if this happened to be in a basic solution, you would see that this hydronium cannot exist. So in order to fix that, you add hydroxides to neutralize the hydronium. Just like mathematics, though, we can simplify like terms and cancel out spectators. So in this case, 14 waters were produced. Those 7 were already here. So we want to simplify by taking away 7 of these. And that's what happened. And now our overall balanced reaction in a basic solution for this one is as you see here. So if you go to our table 18.1 in your textbook, you will see a bunch of half reactions there that you can put together in any fashion, but they will be specific as to an acidic or basic environment. So now go ahead and we'll try another example here. The unbalanced equation is given in the word equation up here. After identifying oxidation numbers, half reactions are written. Iodide is -1, iodine is 0, manganese is +7 in permanganate, +4 in manganese 4 oxide. Now that we know that, we have to balance the half reactions. That's what you see here. Balance the oxygens in the permanganate reaction with the waters. Balance the hydrogens with hydroniums. Now this half reaction, this is our reduction half reaction, RIG, because it was +7 to +4. And then this one was up here was our oxidation reaction. So these look good. Now we have to add them together, balance our charge with our electrons. This was 3 electrons because 7 to 4 is 3. This one, the oxidation was 2 because -1 to 0 is 1, but we had to multiply it by 2. So we're going to have to fix our electrons. You see, once we want to add together, we have 3 times 2 and 2 times 3. Then our electrons will cancel. And then once we've done that, we are in an acidic environment. We have to fix that with a basic and by adding hydroxides. If you recall, this was in a basic environment. So when you do that, they add up to make waters, and then you simplify your waters. Now, hopefully when you do fun sheet questions 18A, questions 1 and 2, try to go ahead and follow these types of steps, and then you'll hopefully be able to solve any balancing of a redox reaction problem. Hopefully you can hear this better, and we'll talk to you soon.